Okay, hi everyone. In this video, I'm going to talk about some of the basic components and structure and operation of the mass spec. So we have a little bit better idea on how this instrument actually goes about detecting these fragments. Okay, so this is a block diagram of a mass spectrometer. Basically, we take our sample and we inject it into the system somehow. Usually our sample is a liquid, but in this inlet system, the sample must very quickly be turned into a gas. And so that means that we're injecting very small amounts. And there are spectrometers that allow, or mass specs that allow you to inject solids, but no matter what the approach, it must be turned into a gas very quickly. We have to keep our sample as a gas. And all of this is under vacuum. So that means very low pressures. That's not how you spell vacuum. Once we get our sample into the mass spec as a gas, it proceeds into what's called the ion source. And so now we're going to take this gas, these are neutrally charged. In the ion source, we're going to make our gas molecules positively charged. So, in other words, we need to create ions. From there, our ions now go through the mass analyzer. And so this is whenever we separate by mass. And then these ions are detected by a detector and processed and displayed on the computer. Okay, so this is a little bit of a more detailed picture of what's going on. So from the sampling reservoir, we start off with our gas, and these are neutral molecules. One way of creating ions is to use an electron beam. And so this is what we would call an electron impact source. And what that does is these neutral molecules go through this electron beam, and then they turn that electron beam, adds and removes electrons, making these molecules into ions. These ions then go through this curved magnetic field. Well, this is one approach. This is the old school traditional approach, is that we run these ions through this curved magnetic field. And so these ions have to turn in order to make it through this path. And light ions, they turn a lot in the magnetic field because it doesn't take as much force, magnetic force, in order to move these ions. And so they're light and they turn too far and they run into the wall. And likewise, it takes a lot more magnetic force to make the heavier ions turn. And these ions, they don't turn enough. And so they run into the wall and they do not get through the mass analyzer. And so what this this magnetic field is doing, it is selecting specific masses of ions. So this magnetic field can work a lot like the monochromator. Depending upon the strength of the magnetic field that we apply, the different masses of ions are going to make it through in order to reach the detector. And also, like in spectroscopy, the detector is an electron multiplier detector. And so the ions hit the cathode, causing electrons to eject. And just like the PMT, the photomultiplier tube, we are going to amplify each ion into multiple electrons, thus multiplying the signal that we get. Okay, so at the beginning, we have to create one of the big first steps of this process is creating ions. There are really two ways to get our sample into the system. One way is a gas phase. So we inject a liquid sample or a solid sample, and we vaporize the sample, and then we ionize it. Another way is a desorption process, and this is whenever you put a sample onto a plate. So you coat a surface with your sample, and then you hit your sample with usually a laser, a high energy laser. And coming off of the sample are ions. And so a desorption source takes your sample and directly converts to gaseous ions. We're going to focus on gas phase sources because this is what we have in the lab. Okay, so some names of gas phase sources are electron impact, chemical ionization, field ionization. Turns out there are lots of different ways to create these ions. Desorption, we've got field desorption, electrospray ionization, matrix-assisted desorption, plasma desorption. Again, there are lots of different techniques and methods of creating these ions. So when we create ions, we really divide, because there are so many types and so many different approaches to creating these ions, we classify our approaches between hard sources and soft sources. Hard sources create lots of fragments. These fragments have charge to mass ratios less than that of the molecular ion. Examples are electron impact. This is the mass spec that we've been looking at in the POGL and the mass spec that you collect in the lab. These are electron impact mass spec. You get lots and lots of fragmentation. Another somewhat hard ionization method is chemical ionization. And this is a pretty rough chemical reaction. And so you put in some sort of molecule that's highly reactive, and that molecule bombards through your sample and creates lots of ions and lots of fragments. Soft sources are things that are processes that create ions with very little fragmentation. The spectra that result really show the molecular ion, and that's about it. Really soft only show the molecular ion. So MALDI, this is a laser desorption process. MALDI is one of the softest forms of ionization. ESI, this is electrospray. Electrospray ionization is basically statically charging your molecules. And so we spray a liquid out and we let the droplets get so small that they become statically charged and become basically single molecule sized. And so that does not result in very much fragmentation at all. Okay, so here I'm going to show you what I mean. What I've done is I've taken the same molecule. We've got this long alcohol and hard ionization. This is probably an electron impact method. Notice that our molecular ion at 158 doesn't exist. Whereas soft ionization, we get the molecular ion, okay, minus a hydrogen, but okay, we can deal with losing a hydrogen. Our base peak is just missing this alcohol. Whereas the base peak in hard ionization is missing pretty much everything except part of the carbon chain. And notice that the smallest fragment, the lightest fragment that we got in soft ionization is 70, whereas we got fragmentation all the way down to 41 in hard ionization. And notice in soft ionization, we're really getting very many fewer fragments going on. And that's the really big piece. So hard ionization creates lots of fragments. You're really mean to your molecule. You break it up into smithereens. Soft ionization works to keep your molecule together in a lot of ways. Okay, so now let's talk about the mass analyzer. This is really the monochromator of the mass spectrometer. It's how the ions are separated by M to Z ratio. And this original sort of mass magnetic selector with this curved path letting in some ions through and causing the others to be too light and run into the wall or be too heavy and run into the wall. This sort of magnetic selector is very high resolution. It really only lets through one mass at a time, but it's very slow. We must scan the magnetic field and allow each mass to hit the detector one at a time. And so that causes this to be slow. So in order to deal with the fact that the sort of curved mass analyzer where we adjust the magnet and we let one M to Z ratio through the analyzer area at a time, because that is so slow, we started working and we developed this method that's known as the quadrupole. And the quadrupole is actually what we have in our lab. And the quadrupole is a lot harder to understand, but it means that what it gives us is lower resolution, but much faster analysis. What happens is we have four rods, four sets of magnets. So hence the quad. the quadrupole. So we adjust the magnetic field between all four of these. And we send our ions in, and our ions start oscillating between these quadrupole fields. And if the M to Z is right, the ion oscillates and stays in a nice stable trajectory and makes it to the detector. If our ion is too heavy or too highly charged, its oscillation becomes unstable and it runs into the magnet and it doesn't ever reach the detector. And what this allows us to do is it allows us to get through a range of M to Z ratios with each set of settings of the magnets rather than just one at a time. Another type of mass analyzer is a time of flight. The time of flight is really low resolution. We don't know the masses that come through the time of flight very well at all, but there's no limit on the masses that we can analyze. So this means that time of flight can get used for really heavy things like proteins. And what happens is we send our ions in and we let our ions fly and we track a start time. And then as we get here at the end, we put this reflectron, so basically a set of magnets that turn this ion around so that it comes and it hits the detector. And what happens is light ions travel faster, and so they hit the detector sooner than heavy ions. So heavy ions are going to take a longer path. It's going to take a lot more to turn them around, and so they're going to hit the detector later. And so what we can do is we can relate the time that it takes for our ions to go from the starting gate to the detector. We can measure that time. And from that time, we can translate that to a mass to charge ratio. So the longer it takes, the heavier the ion. The less time that it takes, the lighter the ion. So when things reach the detector, they hit an ion detector, which is really the PMT for ions. Ion detectors are going to respond and create a signal no matter what ion hits them. And so what we are going to have to do is we have to use that mass analyzer to only let through a certain number of ions at a time to be able to know what M to Z that we're working with. This is just like how the PMT responds to any light that hits it. So we use the monochromator to only let through certain wavelengths of light so that we know what we are detecting. There's also what's known as an array detector for ions, and this is basically a whole set of these that sort of separate out and can monitor multiple masses at a time. Now, I'm not going to go much into this, but the 2002 Nobel Prize in Chemistry was about how we were able to combine a liquid chromatography with mass spectroscopy. And the really, really amazing part that this even worked is that we start with high pressure liquids, and in the mass spec part, we have vacuum, low pressure, gases. And to go between these two components, we use a set of skimmer cones and electrostatic. And this is going to be an electrospray ionization method going on between the liquid chromatography and the mass spectrometry. And so basically what happens here is that the liquid gets sprayed in through a filament, which creates these droplets that are charged. And as these droplets move along, these droplets break apart, and eventually, before it hits this is into the mass spec, we basically have gas phase ions because these droplets have broken apart into such fine mist that we have statically charged ions. And that's how we go from this high pressure liquid state to a low pressure gas state. And this intersection between these two techniques has revolutionized analytical chemistry, and it is a engineering masterpiece. The fact that this works is absolutely amazing. And it's what Nobel Prizes are given for, are updates that technology changes and updates and discoveries that are applied throughout so many different areas of science and really revolutionize the field. And being able to do liquid chromatography and mass spectrometry is one of these sorts of technological marvels of our lifetime. So in lab, you are using the GCMS, and ours, we inject our sample into the injection port. And in our injection port, this is where we create our gas, where we take our liquid and we create our gas. Our gases travel through this column. And once it makes it through the column, separated out into its individual components, it goes through what's called the transfer line, which is really just the line between the column and the mass spec. And then those samples go through the mass spec, and ours is a quadrupole, like is what's drawn in this diagram. And so we ionize our molecules, we run them through the quad, and we detect them. And out comes our different M to Z ratios. So we're going to talk more about chromatography in the next unit and really go into how these chromatographies are working. But this should give you some idea on how mass spec is working.